Hello everyone, I am Pragya Srivastava. I am going to record a lecture on control system KEC 602. So in my present lecture, I am discussing about its unit 5, which is frequency domain analysis. So previously we have discussed about various methods using Bode plot, polar plot and Nicholas plot. In this we will study some frequency domain specifications, and we will study that how the transfer function bandwidth, the frequency response plots, and they are related to each other. We will study the advantages and then we will study some examples. Now, the frequency response of a system is defined as steady state response of the system to a sinusoidal input signal. So we are giving some sinusoidal input signal, and to that input signal we will have, let's say this is the sinusoidal input signal. So previously we will have some transients. So after that transient, the system will get settled. So after these many transients, the system will get settled. So we call this transient and the steady state analysis as a part of response. So frequency response is the study or is the analysis where we are just evaluating the steady state response. If a sinusoidal signal is applied to the input to a LTI linear time invariant system, then it produces a steady state output, which is also called sinusoidal signal. The input and the output sinusoidal signals have same frequencies but different amplitude and different phase. So we are substituting S as G, we are substituting S as J omega, since because S is equals to sigma plus J omega, and this is nothing but 0. We can represent J omega in terms of magnitude and phase. So this thing can be rewritten in two parts. So first is magnitude, we have already studied, and another is phase. So magnitude is this and phase is this. So we are studying magnitude and phase. Now, what is the variable here? Omega. So for different values of omega, we will have different magnitudes, we will have different phase. Now, the amplitude of the input sinusoidal signal is obtained by multiplying the amplitude of the input sinusoidal signal and the magnitude of Gj omega at omega equals to omega 0. Similarly, the phase of the output sinusoidal signal is obtained by adding the phase of input sinusoidal signal to the phase of Gj omega at omega equals to 0. So here we can see that we are talking about amplitude of the input signal, and then we are calculating about omega, which is angular frequency of the sinusoidal signal. We can rewrite angular frequency, of course, as omega will be equal to 2 pi f. So omega naught will be equal to 2 pi f naught. So f naught is the frequency at which the input sinusoidal signal is prevail. Now let's talk about frequency domain specifications. So first we have resonant peak. So it is the maximum value of closed loop transfer function, that is called resonant peak. Resonant frequency, it is the frequency corresponding to this peak which we have just studied. So frequency at which the resonance peak is occurring. Bandwidth, the range of frequencies at which the system normalized gain is more than -3 dB. Now what is the cutoff rate? It is the slope of the log magnitude curve near the cutoff frequencies. Gain margin is the value of gain that may be added to a system in order to bring the system at the verge of instability. So if at all somehow in some conditions we add this much of gain, the system may become unstable. So the margin stability is the phase margin is the additional phase lag that may be added to gain crossover frequency in order to bring the system at the verge of instability. So corresponding, just as for gain margin, phase margin, we have gain crossover frequency and phase crossover frequency. So phase crossover frequency is the frequency at which the phase of open loop transfer function is 180 degree, and it is called as phase crossover frequency. And the gain is where the gain of the where the magnitude plot or where the gain of the system is 0 dB. So gain crossover frequency is a frequency at which the magnitude of the open loop transfer function is unity. So we can say magnitude is unity, or when we talk about gain, that is 20 log. So 20 log of that magnitude, of 20 log of that magnitude, which is 1, that is 20 log 1 is 0. So if we talk about gain, so gain should be 0. If we talk about magnitude, that should be 1. Now transfer function, it is the ratio of CS by RS. So we have studied the most appropriate form of representing a second order transfer function is omega square by s square plus 2 zeta omega ns plus omega n square. So here we are substituting s with j omega. So we can write it as omega n square divided by j omega square plus 2 zeta omega n j omega plus omega n square. Now here we can see that since this here we have this j omega square, so j omega square makes it minus of omega square. So minus of omega square, we are trying to take the omega n common out of this terms. So we are taking out omega n square common. So when we are taking about omega n square common, so it is here for this term we have 1. For this term we have minus omega square by omega square n. Then for this term we have minus j zeta omega by omega n. Now this cancels out and the resultant transfer function is 1 upon 1 plus omega square by omega n square as the real part plus j 2 zeta omega by omega n as the imaginary part. Now we can substitute this complete thing omega by omega n as u. So we can write it as tj omega will be equal to 1 upon 1 plus u square plus j 2 into zeta u. So from here we can have the magnitude as root over real square and imaginary square, and then we have phase information as minus, since it is the term coming out of the denominator. So we have minus tan inverse imaginary by real. So imaginary is 2 zeta u divided by 1 minus u square. So this is the study of transfer function. And then as we have previously studied that frequency domain analysis of a system can be carried either analytically or graphically. So the methods which we have already come across is Bode plot, polar plot, Nicholas and MNN circles. Frequency response plots are used to determine the frequency domain specifications to study the stability of the system. Now here comes the advantage. Transfer functions which are complicated to determine the behavior of experimentally can be, which are like complex, and it will be 2 or 3 times inefficient and non-reliable method to estimate the performance. In that case, we compute and we use to determine using frequency response analysis. Design of a system and adjusting the parameters of system can be easily carried out, and then the corrective measurements can be taken up for noise disturbance generation in the system, and the parameter variations can be easily determined using frequency analysis. Here and all, absolute and relative stability of closed loop system can be estimated from the knowledge of open loop system. Also, frequency domain analysis can be carried out of the non-linear control systems. So in this, presently we have an example where a system is said to be a third order system, and which is showing a resonance peak of 2 and the resonance frequency 3 radians per second. So at 3 radians per second we have a resonance peak which is having a magnitude 2. MR is 2. Determine the transfer function of the equivalent second order system, and then we have to find out TR, TP, TS, that is rise time, and we have to calculate the delay time and the settling time, the overshoot time, and time of oscillation, number of oscillation before settling, and then we have to draw a sketch of step response and the frequency response. So for this, MR is given 2 and omega R is given 3. So omega R is root omega n root over 1 minus 2 zeta square. So from here we have MR is also given. So we can equate this to 2. So we are equating 2 is equals to 1 by 2 zeta root over 1 minus zeta square. So squaring both sides, we get 4 will be equal to 1 upon 4 zeta square into 1 minus zeta square. So from here we get the value of zeta to be, we can have the two values, either 0.669 or 0.993. So we are now again entering into a situation where omega R, so omega R we have been given the value of omega R as 3. So now we can calculate, now omega R will be omega n root over 1 minus 2 zeta square. So from here we can see that omega R is given to us, that is 3. So when we are substituting the value of zeta equals to 0.255, the omega n is coming out to be 3.223, and then the transfer function is, we know that omega n is omega n square s square 2 zeta omega n s into omega n square. So now we know zeta also, we know omega n also. So this is the required transfer function, that is the required second order transfer function. So second order transfer function, the appropriate model we know. Now for this appropriate model we have to fit all the values. TR is pi minus theta by d. So theta is nothing but tan inverse root over 1 minus zeta square by zeta. So from here we can calculate the value of theta. So theta has come out to be 1.3 radians. So we have this value of pi minus theta, and omega d is omega n root over 1 minus zeta square, which is 3.11. So from here we can have the value, we already know the value of pi, we have theta, and where we have omega d. So TR is 0.592 seconds. Now TP is pi by omega d. Pi can be divided by 3.11, and then it is 1.01 seconds. Settling time is always 4 tau. So 4 tau, this time constant is 1 upon zeta omega n. So plus 2% error, we are taking it as 4 tau. So it is 4 upon zeta into omega n. So this is all the variables which we have calculated. Now we have to calculate maximum overshoot, that is MP. So MP is e raised to the power minus zeta pi divided by root over 1 minus zeta square. So this value already can be calculated, and it is 0.8417. So e raised to the power minus 0.8417 is 0.4309. So this is the maximum overshoot. So we can see in the question we were asked the overshoot we have calculated. We have calculated this time domain parameters, and with this we have successfully completed numericals. And now they want us to sketch the response. Sketch the response means, let's say to sketch the frequency response, the estimated time, we have to make that the maximum, this is the value of omega, this is the value of peak. For this peak we should have a resonance, we should have the resonant frequency. Now at this we must tell and initialize our system to get settled. So this is how we can estimate the overall diagram, and particularly in this question, the second order system, the overshoot is given. Here we can see when we have overshoot and the period of oscillation is 0.2 in step response. So we have to calculate from here, from this equation itself we can calculate the value of zeta using natural log. So in this question we are calculating the zeta as this. Now the value of t has been given. For this, fd can be calculated like this. For particular value of fd, we have omega d as 2 pi fd, and we get the value as omega n as 32.16. So now once we have zeta, we can calculate resonant peak using this formula, and also we can calculate resonant frequency omega r using this formula. So this is how we have to rearrange the use of formulas, and we have to implement the same equation to solve the particular desired matrix. In this present equations, we can see that bandwidth, we are equating the minus 20 log root over the quantity equating to minus 3 dB. So when we are equating it to minus 3 dB, we are knowing the value of omega n. We also know the value of zeta. We can calculate the value of omega, and now here it is the fourth order equation, and from the solution we can calculate the value of omega. So this will give us the different frequency domain parameters, and we can, using all these formulas, we can solve the various examples and illustrations which have been discussed just in the slides. Thank you.